yalnız dediğim gibi şeyden bölüm web sitesindeki sınav takvimine de bakın mutlaka. Çünkü orasının güncellenmesi lazım. Ben ona henüz haber vermedim. Okay. So last week I started talking about state space representation of dynamic systems. So this is really an important topic, and I will continue with that topic. Okay, so let me. Okay, so what we do here is we express the differential equation for a system in a different form. Okay. By the way, have you used this concept before, the state-space representation? No. So what I mean is you have an nth-order differential equation, and you express that equation in terms of n first-order equations. Okay. Okay, so that's good to know. So then that means I shouldn't really worry too much about this. So suppose that you have a dynamic system. So you have an input to this system, and then so the input should be u, and there's an output y, and the relation between that is represented in the form of a differential equation. Okay, so first let's consider the most general case, in which case this can be a nonlinear differential equation, right? So in that case I can write this in terms of a general nonlinear function. So I can also write this equation in implicit form, in which case it will be, and I should call it a different name, Fi. Is equal to 0. Okay, so this is the differential equation of the system. And if you remember what I said earlier, for physical systems, the highest derivative of the input signal should always be less than or equal to the highest derivative of your output signal. So that means m should be less than or equal to n for physical systems. Okay, so this is the original differential equation. We express this same equation in terms of n first order differential equations. And to do that, we first need to define these variables. Okay, so we need to define n variables. So this is the second equation, and this is the last one, and so this is one of the most critical steps, defining the state variables. So let me write an explanation here. State variables is a very important step. These variables should be defined in terms of the original inputs and output variables u and y and their derivatives up to n minus 1 and m minus 1. So that means the highest derivatives, the highest order derivatives in the equation should not be used. So what I mean by that is the nth derivative of y and the mth derivative of u should not be used while defining these state variables. And another important point is that while defining the state variables, you should make sure that all the terms, I mean these terms, y, y dot, and derivatives up to y, m minus first, and u dot all the way up to u m minus first derivative şöyle kötü olacak. Şöyle yapayım. Should be represented in your state variables. So that means you cannot define all your state variables in terms of the lower derivatives only. So if n is your highest derivative, then the n minus first derivative should be represented while you choose the state variables. In your state variables. Okay, so let's take a look at an example for. So let's remember the pendulum example. So the equation we have for this was the following, if you remember. So I times theta double dot minus m times g times L over 2 times sine of theta is equal to the Tc, where Tc was the external torque applied. So this is my input, and for this system m is equal to 0 and n is equal to 2, right? Okay, so if you consider what I wrote before and look at this example, then we should define in terms of what? We should consider the output variables up to the n minus first derivative, but since n is equal to 2, we should go to the first derivative. So that means we should define the state variables in terms of y and y dot. And we have m is equal to 0. So we should include the input terms up to the m minus first derivative, but since m is equal to 0, minus first derivative doesn't make any sense. So we don't need to include u. In fact, we should not include u in our state variables. Should not be used. Since m is equal to 0. Okay, so we should have two state variables since n is equal to 2. And the most natural choice for these state variables is the following. We choose first state variable as the first, as the system output, and the second derivative as the but y, there's no y here. The equation is in terms of theta, right? So maybe I should fix that in terms of theta and theta dot. Okay, so let me just say that this is the most natural choice of state variables, and it always works. So if there is no reason to choose state variables differently, you can use this way to define state variables. Okay, so it's not a very good sentence, but I guess you understand what I mean. So it's a very good tip. So if you have an nth order system and you need to choose n state variables, you can just immediately choose this state in this way. So you start from the first, the original system output y, and then you define the following state variables as the derivatives of the increasing derivatives of that output variable, and that always works if your m is equal to 0. So maybe I should. Okay, so let me just quickly complete this example. So these are my state variables. Now I need to write the state equations. Okay, so the state equations are they're just the derivatives of my state variables. The first equation x1 dot is equal to theta dot, and x2 dot is equal to theta double dot. So these are not state equations yet, because they are functions of original system variable theta. I should write these equations in terms of xn and u. Okay, so the first equation is easy because theta dot is equal to x2, so I can write it in terms of state variables very easily as x1 dot is equal to x2. So this is my first state equation. The second equation is x2 dot is equal to theta double dot. convert this into a valid state equation, I refer to the original which was this equation. Okay, so from here I can write theta double dot as 1 over I times Tc plus mgl over 2 sine theta u plus mgl over 2 sine of x1, right? So now my state equations are the following. x1 dot is equal to x2 and x2 dot is equal to mgl divided by 2 times the moments of inertia times sine of x1 plus 1 over I times u. Okay? So these are the state equations for the states defined as above. So notice that the original system is nonlinear, and so is the second state equation. So because of this sine function, this is a nonlinear equation. Okay, so it's a nonlinear differential equation, just like the original system equation. So one of the confusions students have here is that state space representation is applicable for linear systems only, which is not the case. You can write state equations for nonlinear systems as well, and this is an example to that. Okay? Okay, do you have any questions? Bu bir önceki derste bahsettiğiniz state denklemlerini gördük diye. Orada bu state değişkenlerinin, durum değişkenlerinin seçilmesi konusunda da bir şey yapıyordunuz değil mi? Yani onu siz mi oluşturuyordunuz state denklemlerini? Bir gönüllü arıyorum, cevap verecek. Aha, tamam. So as I wrote here, this is a critical step. You know, how you should define these state variables is an important step. And as I wrote here, if you have no other reason, then just go ahead and choose your state variables this way. So it will make your life easy. Okay, now let's consider another example. This time let's consider a linear system. So let's consider a spring mass damper system. For this system, we have the system equation as my double dot plus py dot plus ky is equal to some function f. In fact, the previous example is not complete yet. You know, writing the state equations is by itself is not sufficient. So I forgot that. So I should go back there. So we also need to give the connection between the system, the state variables, and the original system outputs, theta. So there should be an equation like y, which is equal to the theta angle, and we should write this in terms of the state variables, and in fact it is equal to the first state variable. As we defined here, the output is equal to the first state variable, so is equal to x1. And this is the output equation. Okay, so let's consider this second example. This is a linear system, so it should be really easy. So the input is the force applied, and the state variables are, so let me go ahead and choose them as follows. Why that? Because here we also have m as 2 and m is equal to 0. So based on this information, I can, so for input, so this is really obvious, the input is equal to that. But the state variables, as I said before, so this is the most natural way to choose them. So let me just do that. So I guess just directly write the outputs, since these steps are very straightforward here. X1 dot is equal to X2 bilgisayarda bugün bir tuhaflık var ya. X2 dot is equal to, so what is it equal to? It's minus k over m times x1 and minus b over m times x2 and then plus 1 over m times u, right? And the output equation y is equal to x1. Okay, now let's consider a different choice of state variables. Normally, well, I guess I already told this, there's no need to write this one more time. So normally you don't really need to look for, just weird ways to define state variables. But just to give you an example, I'm just going to show you another choice of state variables. Let's this time choose u is still the same. It's the input force. And now let me choose x1 as y plus y dot and x2 as b times y dot. And as I said before, this is not a physical variable anymore. So it's just position plus speed. Okay, so suppose that for whatever reason you are asked to write state equations by using these state variables. So the procedure is the same. So I should write the derivatives of these state variables. X1 dot is equal to y dot plus y double dot. And then the second state equation should be x2 dot is equal to b times y double dot. And as always, these equations are not acceptable because I should write the right hand side in terms of state variables. Okay, so by using these state variable definitions, I can write y dot as 1 over b times x2 and y as x1 minus y dot, but for y dot I can use this one x2. Okay, so I already wrote these y and y dot terms in terms of state variables, and if I write y double dot as well, I will be down here, so I need to write y double dot. It's 1 over m times u minus b y dot minus ky, and that's equal to 1 over m times u minus x2 minus k x1 plus okay, so if now we have everything we need to write the state equations, right? So for y, I'm going to use this one in terms of state variables. For y dot, I'm going to use this thing, and for y double dot, I'm going to use this thing. And if I do all of that, I get the state equations as follows. Minus k over m x1 plus minus 1 over m plus k over bm plus 1 over b times x2 plus 1 over m times u, and x2 that should be okay, I think that's this one, b over minus b k over m and plus b over m times u. Okay, so these are the two state equations, and I should write the output equation y, and that is equal to, where is it? x1 minus y dot and y dot is this thing, so y becomes x1 minus 1 over b times x2. Okay? So as you can see, the equations we obtained are quite different. So the first set of state equations were these equations, and then the output equation was this one. But if we choose the state variables in a different way, as you see here, then these state equations become these equations you see here. So they're obviously not the same equations, they are different equations, but they represent the same system. So if you apply an input here, and if you calculate y by solving for these equations, you obtain exactly the same thing. Okay? Do you have any questions? Okay. So I should warn you though. So this, I just chose these variables randomly. Okay, so there's no reason to choose these. So there's no physical explanation of why I chose these variables. It's just I just wanted to give you an example. But I was careful. I included both y and y dot terms here. So this is required, as I wrote here. So that you should always remember that. So you should make sure that all of these terms are represented in your state variables. So what I mean by that is, so for example, this wouldn't be a valid state variable definition. So if I didn't include that y here, so the first state variable is y dot, and the second state variable is b times y dot is not a valid definition because y is not included there. So I should have y included somehow while choosing state variables. Okay. Do you have any questions? Okay, so maybe we can stop here. Dersin başında demiştim ya size çok güzel bir ders hazırladım diye. İşte o zaman böyle oluyor. Hiç soru falan gelmiyor. Her şey olması gerektiği gibi anlatılınca haliyle. Şimdi şunu kapatayım. Bir